Right, I think we should start. So, first of all, sorry for the delay in starting. Second, I owe you a big apology for not finishing grading the midterm. I know you are all anxious to see the score, and probably I shouldn't go home today until I finish grading because I'm that close to finish. So I promise I'm gonna get it to you as soon as possible.
Just give us a preview from where you're at.
I feel so guilty already. So I already offered something freebie, which is, I mean, you have to work a little bit for it, but it's 5%, 5% extra that you can get. That's a big deal. So what is it? So if you go to the assignment, you will find something called B extra credit. So that is 5% extra credit, and it's unfortunately due next week, together with project 4. But it's gonna be so easy, and you can get 5% for doing it. So what is it? So MATLAB has training modules that's available for anyone. And those are available on something called MATLAB Academy. So if you click on this MATLAB Academy at mathwork.com, you will find out a bunch of modules. I just want you to take the first one. The first one will take only 2 hours of your time. Okay? So it's much, and it's so primitive. You know, it's like, you know, what is MATLAB file? What is, how you can specify a variable name? But it's just a start, so that then you can, if you want later on, you can do other more like long one. Like this one will take 25 hours. And actually at the bottom of that page, when you open that link, you can see they have other courses you can click on. And there's a lot of things for automatic control and solid mechanics. There's bunch of modules that can really be very helpful for you. But to get 5% from now until next Monday, you can just spend 2 hours in doing this. So once you go through them, they will give you a certificate of completion. Okay, one, you can put it in your resume, say finished a training course on MATLAB. And second, you will upload this, I guess in PDF format or something, or an image or whatever. You will upload it to the assignment box. Okay, so one, this will get you started in basically doing or like achieving all those MATLAB training module. And second, you get 5%. So I think it's a good deal, right? Yes. Okay. 5% of the course grade. So this is actually as if you missed like a project, this would be as if you didn't miss the project, right? So so in the grade right now, when you finish this, you will just get yes or no that you did complete this assignment. But then I will remember at the end of the semester what I'm gonna do. I'm gonna take off your lowest 2 homework, and I'm gonna take off your lowest 2 quizzes and your lowest 2 project. And if you did this, no, lowest 1 project. I said lowest 1 project, but this would be your chance to get extra 5%. So I mean, with all those extra stuff, no one should get a C. I bet everyone will be a B or higher.
I did have a question. I think 2 weeks ago you said that you were going to take the lowest project and make 100. Are you going to drop, or are you going to make 100?
So I think easier for me on my Excel is to just go for the lowest one and just mix it up to 100 rather than deleting it. I think that's, and it look nicer this way too. It will show in your grade that you basically got higher. So, but I'm the same thing for the homework and quizzes. I'm just gonna go for where is your lowest. If you missing 2, I'm just gonna get 10 and 10. If your lowest was like 0 and like or 0.1 and 1 and whatever, I'm gonna take them up all the way. Okay, and so this I will see who did this, and I'll give him just extra 5%. So it'll be a lot of points to celebrate. All right. So now remember this last week. Does anyone remember this graph?
Yes.
So what is this graph? Cross flow like radiator, right? Fluid is going this way in the pipes and the air is going normal to it. And I was confused last week about like which one is the black solid line and which one is the dotted. Like here in this one, there's no confusion because both fluids are this one in that cartoon. Both fluids are unmixed. Both fluids go into pipes, baffles. They are not going as a bulk. It's not a stampede of fluid. Let's all go, guys, get heated. No, everyone going into his own lane. Okay, but this one, in this cartoon, they wanted to say that one fluid is unmixed, going into pipes, going into baffle, while the other fluid is just like, let's go. Everyone go in this big duct together. And I was confused which line belonged to which. Okay, and I told you we need to find a better chart where they actually have the key. This is the better chart which has the key. So what is the key? The solid one belong to C minimum is the mixed, and the dotted one is C max is the mixed. Okay. Then you will so of course when at the end C mixed over C unmixed, this curve, the one on the top, this curve is universal in any configuration. This is a curve where one of the guys in the heat exchanger is what? Going through a phase change, and therefore his delta T is 0, and therefore his m dot Cp is infinity. I mean, if we're gonna stick to the law that say Q is m dot Cp delta T, which is not really appropriate when you have phase change, because like what delta T are you talking about? Delta T is 0. I'm just going from liquid to vapor or vapor to liquid. So what delta T are talking about? But those graphs are designed for, you know, they are all those graphs are done for what is your capital C? What's my capital C? M dot Cp. So they want m dot Cp. So this curve then belonged to one of the guys in the heat transfer are having m dot Cp infinity, right? And so that's why, because they are saying, they are calling it C mixed over C unmixed, it become 0 or infinity, right? Because really the minimum, the C dot, the capital C minimum is the one that will not be infinity. The other one will be infinity. So that's why he's calling it 0 infinity, 0 or infinity, depending on which one is the minimum, the maximum, the max, or the mixed or the unmixed, right? So what I'm saying is, last curve, don't worry who is mixed and who isn't mixed. This last curve, whether the minimum is mixed or whether the maximum is mixed, whether it doesn't even matter whether it's your cross flow or barrel flow. That curve eventually become one fluid is not doing heat. One fluid is not going through temperature change. One fluid is just doing phase change, right? So it doesn't matter barrel, counter, cross flow, who's mixed, who's unmixed. What happened is one fluid is changing its temperature, while on the other side of the wall, whatever that wall look like, barrel, counter, cross flow, the other side of the wall, constant temperature. Everywhere we go, on the other side It's always constant temperature. So really what matters is how long is this passage? Not this passage going like this or going up and down or going, doesn't matter the configuration. What matters is how long do I stay in this pipe, because my fluid temperature or my temperature will increase or decrease depending on the area. All right. So I would suggest that you add this. So this is already on. This is already on our canvas, and I would suggest that you put it on, like attach it to the other PDF, right? So just put it next to it. All right. So the exam, the second midterm is gonna be on heat transfer. And we said HVAC, right? And it's not next week. We still have 1 week before the exam. So So 1 more week. All right. So this is the Cmin Cmax. That's the one. So just add this to your, chapter 11 thing when we discuss this. Good. All right. So now homework 7 that was due this week. This guy. Homework 8 is actually. So this is homework 7, which we had 2 problems, right? This guy and the spiral flow thing, and then this kind of boiler, which look very similar to our project, which like one place you are doing sensible heating and the other place you are doing phase change, right? In our project, we are doing the same thing, except that we are adding also the superheat. So sensible heating, phase change, and then the extra superheating. So homework 8 is actually to do this again. We're gonna do the same homework again, same 2 problems, but what? But we are doing it with, can anyone guess? MATLAB. And so how are we gonna do it with MATLAB? So that is what we're gonna do in the first part of this class today. So I see here in chapter 8, he say, in homework 8, you're asked to solve homework 7 again, but this time you have to use MATLAB. You can work in group of 2 students if you want. You don't have to. If you don't like other people and you just want to work alone for the rest of your life, that's fine with me. But I would strongly encourage you to work with other people, even if you think, I got it, I don't need help. It's really, really useful, okay? To talk with other people and communicate with other people, right? And even if you think you know it all and you are the best student in this class, you still benefit from explaining what you think to other people. There's another level of knowledge you get when you try to communicate downwards, right? Because the other person will ask you a question and you need to reiterate your thoughts and like, yeah, why is that? And so again, I would strongly encourage you, but I'm not going to force you. So people online, you can also chat and try to prepare yourself with each other, right? And so how are we going to do this in MATLAB? So same 2 problem exactly, right? And in the second problem, he say, please use the effectiveness method. So I mean, in the second problem, he asked us to use the effectiveness method. So fortunately, the code or the MATLAB file that's available for us actually use the effectiveness method. So there are those 2 guys, and we're gonna talk about them. And here is a homework from 2 years ago that actually specifically use this. So that would be a really good example for us. So here is the homework. This is homework 8 2 years ago, not our homework this week. And here is a solution for it. So what are those two files? There is this effectiveness thing here. Let me open it in my, it's too small, I guess, to see. But if you see this basically, I got this from File Exchange in MATLAB webpage, right? You know, in MATLAB side, there's a lot of codes available. Who has been to File Exchange? All right, did only one person? It's really a very cool place. You can go there and you can, all you need to do is just have a MATLAB account, which is, I think it's for free. So if I just say MATLAB Exchange, right, and you can look for, you know, application, and discipline. You can go to engineering, and under engineering, you'll probably find XTeam over there and stuff, and you can search for things that maybe we wanna see. Modeling of Rankine cycle using, see, that's and XTeam. Here's XTeam. Thermodynamic property of water and steam. Anyway, so I was talking about what is this? So this code effectiveness, if you read it, just say it's number of transfer unit UA over Cmin, and he basically just you go in with the number of transfer unit and the C and the R and the heat exchanger type and the number of pass, and he go and find out, what did you tell me? Did you tell me barrel flow? And then he calculate. What is that? The effectiveness, epsilon. He just calculate epsilon. So that function is basically the table of equation that we saw in the lecture notes. Remember, for each case, there is an equation between epsilon, the effectiveness, and NTU, number of transfer unit, which is UA over Cmin, and the ratio, C minimum over C max, right? So that's what he do. They call it CR. Remember the joke last week, how like everything is C, starting from CB to capital C to the ratio also CR, everything is C. So this just basically go and calculate the effectiveness method for you. The heat exchanger one, it's set up such that when you call this, what do we need from the effectiveness method? Why do we use the effectiveness method? Because we don't know all the temperature, and we really want to know the 2 exit temperature. So we call the effectiveness method if we know the area and the use. So we know, and the heat exchanger type. We have a heat exchanger, and we are telling him we got this hot fluid coming in, cold fluid coming in, and we want to know what is the results. How cold will be the hot fluid at the exit, and how hot will be the cold fluid at the exit. Basically, we need to figure those two guys. So that's what this heat exchanger module will do. He, at the end of the day, he calculate this. He calculate T hot out and TC out. And how does he do this? I mean, that's easy. He basically look for Cmin. He compare the two C that you give him. The C hot and the C cold. He say, which one is C minimum? And once he do this, he also calculate the ratio and the number of transfer unit, UA over Cmin. And then he go and call the effectiveness module. So you need those two guys, heat exchanger and the effectiveness method. He calculate the epsilon, and once he calculate the epsilon, then he basically say, here's my Qmax, which is C minimum time the maximum delta T. What's the maximum delta T? T hot N minus T cold N, right? Those two, the T hot N minus T cold N, that's the maximum temperature difference. multiply by C minimum, then this is the Q maximum ever that you can ever imagine to transfer between the two guys.
So
And-
is that epsilon? Is that from the other file? Is that why we
Say that
get both?
again.
So the epsilon in this file is from the effectiveness. So you need both.
So the effectiveness is basically working as a slave under the heat exchanger master's function. So you definitely need the two functions sitting in the place where you're solving the problem.
All right, that's what I was wondering. Okay.
Right. Yeah, they cannot work without each other. Basically, the effectiveness is really where the calculation is being done for the formula, and the heat exchanger function is the one that basically set the equation so that we can use effectiveness. Setting it basically mean give me my number of transfer unit and tell me which one is minimum. So I can go ahead and use the formula. Okay. And so he calculate the Q actual from epsilon times Q max. And now once I have my Q actual, I can calculate T hot out and TC out. So that is the appropriate way to use the effectiveness method. You use it when you have the area, you have the U, you have the M dot, and you are just wondering how hot will the cold fluid leave and how cold will the hot fluid leave. You are just wondering what will happen. Okay. Now, not every single problem is done that way. Some problem actually ask you for the area. Like our homework. Did this homework ask for the C out and C in, or did he ask for the area? He asked for the area. So how could I solve it with the effectiveness method that's actually cannot start? I'm not talking about number how we can yeah, this one is asking for the area, right? Calculate the required area. So how can I use it solve this where I don't have the area? So in order for the method to start, you need to give me the area. But in this problem, you're supposed to calculate the area. So what happens then? And he said, use the effectiveness method. So what do I do?
Calculate the exit temperatures.
Say that again.
Calculate the exit temperatures for each side, and then you can use the effectiveness method.
I didn't hear that well. Say that again slowly.
If you calculate the exit temperatures,
But I cannot calculate the exit temperature because I don't know the area. There is no area given here. And actually the temperature is given here. When you think about it. See how the cold fluid is coming at 27 and leaving at 122? And the hot fluid is coming at 147, but I bet I can know what's the temperature, right? How can I tell the temperature? Q equal Q, right? Q equal Q, and Q is M dot Cp delta T, and Q is M dot Cp delta T. So I can calculate the temperature. So this problem is not set really well for the effectiveness method. Still, I want to use that effectiveness method module to do that. So what will happen then? Anyone? Any help? How about try and error? Right? I mean, you can set it such that you'd say, I don't know the temperature at the exit. I don't know that he's actually leaving at 122. So you can let him run for different area until you get that 122. Right? And once he gets you to target, you say, done. It's one that was actually the correct area. should have been, 30 meters square, because anything less than this, and so maybe you can have like a small plot or a small table between. Here is the area, here is the temperature, area temperature, area temperature, area temperature. And if you can even put it in a loop, that can fly like this, and you will be done. Okay, so I explained the heat exchanger, but you will not really get it until you see it in action, right? And so a great way to do this is actually look at this example, that homework problem from 2 years ago, which. Yeah, go ahead. Let me get it so that we can all see it first. Okay, ask the question again. Right. Yes. Right. So what the question for people online is that latent heat of vaporization, that 110 kilojoule per kilogram, is that my Q dot in the, see there's two parts, one part without bubbles, one part that just like cold fluid becoming saturated. And then the second part is the saturated fluid is bubbling until it become all vapor. And maybe even superheated, but he didn't, because he said X is 1, right? So the question is, can we think of this as Q dot? And my question for you is, what is the unit of Q dot? What? Joule per second. This guy is joule per kilogram. Joule per kilogram. To turn joule per kilogram to kilogram per second, sorry, to turn joule per kilogram to joule per second, I need kilogram per second. So you should think of this as Q dot per M dot. This is a small q. This is Q added, right? Small q, specific heat addition. So it's just waiting for M dot. It's waiting for M dot. So if you multiply this with that M dot, the 5.2, you got yourself your Q dot over here. Yes? And if we have the Q dot, that the cold fluid, the water, it's not the water, the working fluid, the organic fluid. If we got this Q dot, then we also got this Q dot. I mean, if this is the Q dot that the fluid take to heat, this is also the Q dot this guy will take to cool. And what this allows you to get is the delta T here. You will be able to find this temperature in this part. And so now this now is a separate heat exchanger. One fluid is constant temperature, the other guy is doing this. Right? And he's going from 147 down to whatever temperature you just calculated. Now in the second part, this is counterflow. The cold is going from 27 to T saturation, and the hot is going from that temperature all the way down to the whatever it takes to go down. Yes? Okay. By the way, what is organic fluid mean? It's like all those, it's not steam. And they like those weird fluid at temperature range that's so cold like this. I mean, it's not like 1000 and stuff. Because the dome is really nice. The dome, the vapor dome is really nice. And it allows you to have dry turbine. What's a dry turbine? X is more than 1 at the exit. Dry turbine even without superheater. So remember how in one of the previous projects, when we lowered when we took the pressure up, we end up with a very wet turbine, and we said there, you guys were, your job was, one of the requirements was to find out What's the minimum X that you allow in your turbine before it becomes so dangerous and all those droplets at the end of the condenser, sorry, at the end of the turbine before you go to the condenser become really destructive for the turbine. If the quality of this guy is low, 0.7 and 0.6 and like weird number like this, you'll be shooting droplets tuck, 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 on the plates of the turbine. And that will destroy the turbine, right? So those organic fluid with this small temperature range will be dry because the way their dome is sitting, basically. Okay. Anyway, so let's look at this example here. Homework 8, fall 2018. And it's a, please repeat this example. Here's an example over here. If the heat exchanger type was counterflow, cross flow, neither fluid is mixed. So both fluids are unmixed. That's the first graph. Both fluids are unmixed. Every one go into a pipe. And compare the results of the three type to find out which one is best. Okay, so this problem is perfect for the effectiveness method. Why? Because I got the U, I got the area, I got the heat exchanger, and I have the temperature N and the temperature N. Okay, and this capital C, what is this capital C? That's the m dot Cp, and I could tell because of the units also. Huh? I mean, even if someone give it to you in small font and you're like, is that specific heat or the heat capacity? The unit will give it to you because it's watt per Kelvin. When you remember, like Q is m dot Cp delta T. So Q dot over delta T is m dot Cp. So m dot Cp must be Q dot over delta T. It must be watt over Kelvin. All right? So when it's watt over Kelvin, that's basically m dot Cp. So that would be perfect for that program, right? And so those are the results. So you can practice with that code, and you should produce basically those numbers. TC out, cold, TC. I think I made a mistake. It should say, yeah, T hot, sorry, no mistake. It's T hot out and TC out. And C stand for degree centigrade, I think, yes. So you see for barrel, counter, cross flow, and the Q in each case. And I guess not surprisingly, which one is the best out of those three? Counterflow. Look at the counter, it has 760 compared to 730 compared to 650. That's what you do when you do barrel flow. It's horrible. You're shooting yourself in the feet, basically. Because you put the two fluids against each other and they limit each other potential to go down and go up. So you are submerging your own fluids by sending them into barrel flow. Okay. Now the second problem for a counterflow heat exchanger operating with this temperature, and this C and C, what is the area m square required to bring the hot fluid at 90 degrees? Okay, so that is the one problem that you actually, similar to our homework, where he's asking for the area. And the heat exchanger is not really, the heat exchanger function is not set to calculate area. It's set to calculate temperature out. So that's when you will enter, assume the m dot, calculate the temperature, tell yourself, is that the right one or no? And then you go back and forth, right? And so those are the answers. And the code that does all this, or like one example here, homework 8.2.m. If we open it here, okay, you will see how it is working. So So I'm feeding him the what he wants, huh? CB hot, M dot hot, T hot N, CB cold, M dot cold, T cold N, and the U and the area. And so this is the part, huh? That will be part of the assumption. You assume this until it gets you the right temperature, right? And this is a call for the heat exchanger function. So all those number, those are number. What is the number for M dot hot? It's basically this guy. So rather than writing this, we could have entered 10. But there is something nice about setting your input variable up and then let them run under, let them crunch number underneath. Because then you can basically say, right at this part, and you would say given, right? You would say given over here, and you would under comment like this, right? And you will set I guess you also given. It's the area that was required, and then you try it here required, right? Required the area, and then you will start the solution by assume area equal 19 meters. Okay, and then at the end you would say check, I guess. Like here, check if T out is correct. So I just want to show you how, like in this example, how he is calling the heat exchanger. So you need to give him those things in order, right? So M dot hot, CB hot, and you know that order from this example, or if you go to the function over here, he will tell you, I mean, the names are very clear, right? So that is the thing, that the number where he's expecting it from you. And the last one, HE type, right? He is telling you this is exactly the call. This is how you are supposed to write them. You cannot change the format. You have to stick to exactly those wording, right? And so see how counterflow over here in purple? It's exactly what this, you have to write it exactly the way it is. If it's capital C, you have to make capital C. Capital F, you have to make capital F. Right. So I know you can call a function in MATLAB. That's not really that hard. But for those who are still have been hesitant to use MATLAB, you need to take that step, right? And IIM and the TAs, both of them, would be very happy to help you if you still are having problem. But I really wish that everyone leave this course with ability to easily use a MATLAB code that we can get from File Exchange at least. I mean, you don't have to be a good programmer until you get your 3403, right? 3403 computer method. That's when you'll really become good. But at least for now, what you need to be able is that if someone give you a file, MATLAB file, you can run it. And by run it, you just need to know where the numbers, where the input numbers, and how can you set everything under one directory, keep all the function, and basically let them call each other. Like this example is going to call heat exchanger, and heat exchanger is calling effectiveness. Okay. So when you made that call, things, what will come out? This will come out. The other side is what will come out. Like just like what we did with XTeam and what we did with psychrometric chart. This what will come out. And those two numbers now, he is first turning them into degree C. Ouch. He's turning them into degree C, and then he is calculating Q hot and Q cold. All right? Yeah. So the reason why we are assuming the area is because that heat exchanger code will not run without an area. He required the area and the U as an input, and he extract or produce the temperature as an output. So in order to use it, we really have to work in his own language. Can I solve the problem using the effectiveness method without this assumption? Well, if we have the chart, we can. How do we do that? Well, the UA is actually in the x-axis, right? I'm waiting for my laptop to turn. I can tell you, but the effectiveness, this guy, let's assume it's cross flow. The area is here. This is UA over C min. Okay. So if I just can come down like this and read, and I find out it's 3, number transfer unit is 3, I'll be able to get the area. Okay. So how can I go like this and read? I need this. That's easy. That's m dot CP over m dot CP. And if one of them is doing phase change, even better. It's going to be this curve. Okay. So I got this. Now, do I know the effectiveness? That's the only thing that's missing from me. If I know the effectiveness, I'll be able to come and read basically number transfer unit and find the area. Do I know the effectiveness? What's the effectiveness? Q dot actual over Q dot max. Right? Do I know Q dot actual? Yes, I know, because why do I know that? Because I know the m dot CP and delta T. So I know Q dot actual. Do I know Q dot max? Yes, I do, because I have T hot N and T cold N, that's delta T max, and I know which one is m dot CP minimum. So I really know the effectiveness that I desire from that heat exchanger. So I can come like this and read. So that would be the way to use this chart in the exam next week. No, the week after next week. If I force you to use the effectiveness method to solve that problem in the exam, you will just come like this, find out what's the effectiveness, what's C minimum, and get the area. Right? But it's that heat exchanger MATLAB code that wouldn't let you do this. So that's why, I mean, they could reward, like maybe one of you will do this and publish that in the file exchange and call it, right? If I have time, I will do that too. It would be nice, because that is really needed. So you would call it basically heat exchanger area or something, find heat exchanger area. I found that code totally and couldn't get it to work due to the type error. Yes, so the type error, again, if I were you, first of all, I will let this code run. This example one, make it run first, and it should run. And then after that, you will just modify this from copying this, right? You just copy and paste. You don't even type. Control C, and you would go and put it here, and it will work. Right? Here's a funny and sad story about MATLAB. Like, I remember the first time I used MATLAB, like maybe for 2 weeks, I couldn't make the program run. And it turned out because it was the file name. I like in my file name to put dash and like a version, or dash and the date. So I know like when was this like written. And it turned out that MATLAB don't accept dashes in the file name. It has to be underscore. That's it, basically. For 2 weeks, I couldn't, I'm like, what's going on? And I hit myself and I hit MATLAB. And so, I mean, he's really very picky when it comes to the names and formatting and stuff. All right. So, does this make sense? Yes. So we will run, you guys can run this code basically, this file to just make sure this works. And then for homework 8, you will do homework 7 again with, and so homework 7 basically is 2 problems, right? You'll be able to do this. And so that will be easy, hopefully. Questions? All right. Let me tell you that to prepare for the midterm, there are all those problems. There are 100, like how many problems in here in chapter 3 of that book? Let's go till the end. How many? 44? 44 problems, right? So this is a 44 solved problem that you can practice on. All right? Huh?
That book goes.
The book and its solution is basically here. Download the heat transfer book and solve the exam. Okay, those are the 2 links. So download this and don't look at the solution immediately. Try to solve the problem. Give yourself, a chance to get in pain a little bit, like 5 minutes of pain before you to jump to the solution. Force yourself to like, no, I need to get it myself. All right? Good. All right. So we can spend, if you have more question in the about heat transfer, we can do it in the second part of the lecture. I mean, in the last hour of the lecture, right? Especially if you have question about the project too, which actually happen to be due next week. Right. So the next part of the course is the fluid part. And here is what I'm hoping we can achieve from this part. The pressure, calculate the pressure needed for a given pipe dimension and flow rate.
I'm sorry,
Right.
sir. So on the exam, did you say it's November 1st or a week from today?
So the exam is not next week. The
So
exam
it's November
is
1st.
like
Okay.
1 week from so we have one more class and then the exam. And it should be under the syllabus, right?
Okay, I was just making sure. Thank you.
Yeah, we didn't change the date. Whatever is on the syllabus, it still works. Which is next week? Not.
2 weeks. 2 weeks from today.
Really? Let me double check. Let me check. Here is my syllabus. No, that's not my syllabus. This is my syllabus. It say exam 2 is November 1st, and today is October 18, sorry. So you have one more class next week, and then the exam. Yes? It's over the stuff in red. So it's the psychometric application, all the psychometric charts, right? And what's the temperature of the supply air, and what's the temperature of the air leaving the cooling coil, and latent load and sensible load, all the stuff about the psychometric chart and HVAC, and then the heat transfer. All right? Again, so the question is, are you going to post the solution for the second midterm? Yes. And when are you going to post it? I'm going to post it just the Sunday before that. Why? Because I just don't want you to read it. There is so many solutions everywhere, but I just want you to really experience the time crunch, because that is really a problem, like how quickly you should solve the problems. Can you do it if you promise to solve it on Friday? You promise? Okay, then I'll post it on Saturday. All right. So now in this last part of the course, you know what our goal is to be able to calculate pressure drop in a pipe. If you have this flow rate and you want to deliver it from Stillwater to Tulsa, water pipeline or natural gas pipeline, and they ask you, well, how large is the compressor that drives this natural gas, or how large is this pump? You should be able to calculate the pressure drop. You should be able to plot something called the load curve. So a pipeline or a pipe network, the pumping power is function of the flow rate. There is a curve between them. It's not constant. Depending on how quickly or how large the flow rate is, the pumping power go basically with it. Right? So we need to understand this relation. And then to be able to match a pump to that load curve. What pump is good for this system? All right? And finally, maybe we can make an application and to apply this knowledge to make sure that we understand. And so a ground source heat pump, what's a ground source heat pump? A heat pump, internal unit in your house, external unit outside, but rather than using the air for cooling or heating, they go into the ground with a bunch of pipes. It's network of pipes that go into the ground because the ground is more favorable for heat transfer than the air, because it's warmer in the winter and it's colder in the summer. So who wouldn't need that, right? That's pretty good. That help our heat pump to have a smaller delta T on it, which make the COP go higher. Okay, so that is the plan. And you know, this part, you probably have seen it in which course, how to calculate the pressure. Fluid mechanics, you probably have seen it and you probably remember it too. But so it will be a good review, right? It's not going to be that hard. So how much horsepower does the pump need to deliver the Q from one displace to the other? Okay, so sometimes they ask for the horsepower, sometimes they basically say what is the head of the pump. Okay, so and the head is usually in feet of water. So why does the pump have to work to deliver that? Because every one of those things have pressure drop over it. The inlet with all those strains have pressure drop. The elbow has pressure drop. The T has pressure drop. And of course, straight pipe has pressure drop. And that flow rate, that kinetic energy here is energy that the pump need to work for, right? All that, and you would think maybe that kinetic energy, but it's useful. No, it's not, because all that kinetic energy, what will happen to it in the tank? Will dissipate and become heat. All that exit flow rate is total loss. I mean, you wish you will just like slowly pushing it. Because that if you are sending it at very large V square over 2, big kinetic energy, you are paying for it. Okay. So the losses in these pipes and the elbows and the valve, and so the major loss, which is straight pipe, and the minor loss, they are all basically function on or like depend on, are the flow laminar or is the flow turbulent? Okay. And so the guy who first came up with this experiment was Reynolds. And the experiment was like this, like pipes with a dye. And in the spring, we offer, hopefully we'll offer experimental fluid 4273. And we have one, we do this experiment where we basically, we have like a channel, big channel, and we put the dye, color dye, food dye, so food color. And we put it in the pipe, and you can really see when the flow is small, the dye just like leave nicely. But if you increase the velocity, or increase the diameter, or decrease the viscosity, like rather than viscous fluid, use like very light viscous fluid, you will actually see the dye doing this. And the reason why it's doing this is that the flow is unstable. Any small fluctuation get amplified and you see the dye basically spread. And so once the flow become turbulent, the losses really increase a lot. It takes a lot, as you can imagine, if the fluid is moving nicely and moving in layer, that's super easy to pump. But if you start banging on the tube like this, that takes up more energy, right? So that is horrible from the pump point of view, but it's great from what point of view? To make the flow turbulent, this is great from the point of view of heat transfer and mixing. They love it. They love it if the flow is turbulent. So they really want the fluid to bang against the wall. They love it if the fluid that need to get hotter or colder depending on what is the heat transfer, they wish it like go back and forth, right? And you do this yourself every day when you're making your coffee. Maybe not coffee, but maybe instant coffee. Like you put the powder and you put the milk, and then you do this so that you can help the turbulence to mix. I mean, if we just let it sit with the sugar and we add the water, I mean, we will wait for hours for it to go up, right? When my son, my 8-year-old son, he's actually the pacifist kid who's, I shouldn't say that because my other kids will hate me for it, but like he's very helpful. Like he will just make lemonade for me or my mom and say, here you go, without any reason. But when he put unfortunately, when he put the sugar and the lemonade and the water, he does not mix well. And so you can find all the sugar sitting at the floor, right? Because he does not really know that you need to mix really well. So they mix, well, by doing this, you can buy this, You can those buy, and if you come over to my office in the second floor, you will find that I have a bunch of those pipe inserts that they put them into the pipe so that you don't really have to make the flow go with very high velocity so that this happen. No, you artificially make him do it. So when the flow goes through all this jungle of pipe insert, he's basically doing this, right? Again, horrible. From pressure drop point of view, the pump is paying for this. Right? A lot of horsepower is wasted on this. But if our job is to make this fluid in the inner pipe, the cold fluid in the inner pipe, mix with the outer fluid in the red pipe over a very short distance, and you cannot afford to make your heat exchanger like 20 meters long, that is the way to go. Okay. So we need, no one, what the point behind this is that you shouldn't always think in your design, let's make it laminar so that we wouldn't pay the pressure drop. No, you wanna pay the pressure drop if there's other objective in your head, right? So you may be willing to actually have extra turbulence. So the pressure drop can be calculated like this or like this. And I really think this equation here is probably the most important thing that you need to have in your head from fluid mechanics before you leave college. Just like in heat transfer, the equation that you need to remember is what? From heat transfer course, one equation. It's what? Q dot is UA delta T. Q is UA delta T, and delta T is logarithmic mean temperature difference. That is the equation heat transfer. I would say in fluid mechanics, at least in undergraduate level, that is the equation to remember. That the pressure drop in a pipe is F L over D half rho V square. Half rho V square is called, what's the name for it? It's called dynamic, so close. It's called dynamic pressure, but it's not head yet. When you turn it like this, what happened here? He just divided this the pressure drop in a pipe, he divided it over and rho g. It's rho g. So the head loss is a frictional pressure drop divided by rho g. So when you divide this over rho g, what happened? The rho disappear and the g show up. So now this is exactly this, except that the unit here is, what's the unit of this guy? Pressure. It has to be pressure. Delta P is this. This is Pascal. That's why half rho v square, notice that FL over D, what's the unit of FL over D? FL over D, what's the unit for that? Dimensionless, correct? This doesn't have any unit because L and D kill each other. And F is dimensionless, it's friction factor. F is actually this. F is dimensionless shear stress. So it's the wall shear stress divided by half rho v square. So Pascal over Pascal, F is dimensionless. So point is, half rho v square is called the dynamic pressure. Why is the dynamic pressure? That's all the velocity in terms of pressure. And that's what they really measure by a beaded static tube. What's a beaded static tube? Total pressure poured with a static pressure port. Okay, one that measured the velocity without stopping it, or the pressure without stopping the flow, and one that's basically standing up like this. It's like the one that's sitting in the nose of the fighter jet. You know, they usually have like a beaded static tube on the top, on the front. So the difference between a pressure tab that is measuring total pressure and a pressure tab that let the flow go over it, that's a static pressure, that is half rho v square. Okay. So you multiply. So this is basically all the kinetic energy in terms of pressure. And so you multiply this by FL over D, and that will tell you how much pressure drop there is. So you can see it's function of L over D. So the longer the pipe, the more the pressure drop. The bigger the pipe, the less the pressure drop. So it's really L over D. So a tiny pipe, diameter wise, that's 10 centimeter, could have the same pressure drop as a really big pipe for like 10 meters, because it has the same L over D. Right? So this is in terms of Pascal, and this is in terms of meter, yeah, head, feet, right? So FL over D, but V square over 2G. So obviously V square over 2G is in meter. And that's called the basically the head loss, right? So tell you, well, that pipe is like 5 meter head loss. They don't mean that the length is 5 meters, but they mean that FL over D times V square over 2G is 5 meters. Okay. And so when you look at the pump charts that they sell in the market, they will have this that the pump can deliver on the y-axis. They don't tell you the delta P of the pump. They tell you the head of the pump. They tell you basically this pump can provide 10 meters of head as function of the Q. Here is the flow rate of the pump on the x-axis. Okay. So how do I get the V? Q over area. The flow rate, 10 gallons per minute over area. What area? Cross-section area. By over 4D square. That's how you're going to get my V. L over D, of course, that comes from geometry of the pipe, length and the diameter. Right? So it's the F. Where do we get the F? Moody chart. Yes. The Moody chart. Okay, and we all, if you all remember, the Moody chart has two parts, the laminar part and the turbulent part. Okay. So it's amazing how for laminar pipe, it doesn't matter what is the roughness. When you think about it, it's not really that hard to imagine why, right? Why it's okay to accept that? That for laminar pipe, it doesn't matter what's the roughness, there's just one equation for the F. What's the equation? 64 over the Reynolds number. What's the Reynolds number? Rho VD over mu. Rho fluid, mu fluid in the pipe, V of the fluid in the pipe, the diameter of the pipe. Okay. So no matter plastic, concrete, cast iron, forged cast iron, whatever the pipe, one equation. But then when it become turbulent, which happen at what, Reynolds number greater than 4,000? This is, by the way, Reynolds number smaller than how much? 2,300 is the magic number. So 2,300 laminar, more than 4,000 turbulent, in between, good luck. You don't really know what happened. In between, there's transition. And it's so hard to study because it really depends on the roughness, the geometry. So all those curves, guess what happened to them? All those curves eventually collapse to this, but they don't show you that transition. Like each one of them kind of go like this, you know, like you have like a goose neck and then you go. But it's really hard to study this. And so usually people don't work in this region. Usually you are either here or there. Okay. Yes, if you are here, that's called laminar. Reynolds number is less than 2,300. And at that point, if you track it, it's basically 4,000. So above this, 4,000. And then when the curves start to become straight, this is inconvenient. When the curve becomes straight, what does it mean? It's fully turbulent, huh? And basically that you just have a function number, the F is function only of the epsilon over D. Okay, so two parts, you can get free quiz if you answer those two questions. What is the significance, or like how could you explain this? How do you explain that when the Reynolds number becomes so big, the F that we are reading is just like say 0.3 or like whatever, this is 0.028. It's not important what the Reynolds number anymore.
Because the water's fully turbulent already?
Yeah, but that's exactly my question. Why when the flow is fully turbulent, the Reynolds number is not important? It's similar to basically saying when you are as rich as Bill Gates, it does not really matter how much money you have. Like the thing that defines you does not matter anymore once you become that rich. So back to the point, forget about Bill Gates. Why if your Reynolds number is high, it doesn't matter what's the Reynolds number in calculating your F? Yes. The answer is because maybe the water does not interact with the wall. No, it does. The answer is because the water is only interacting with itself. No, notice that the function here is still function of epsilon over D. What's epsilon over D? What is that? It's the roughness of the wall as function of the diameter. So no, it still interact with the wall. And that's why the F is function of the wall. The friction is 0.002 or 0.02 or 0.05, depending on the pipe material. It still interacts with the wall. It's still function of the wall. But why the Reynolds number is not important? Anyone? I think this is really important to think about. Okay, so I'll let you. Yes, go ahead. The answer is when you look over here, when the Reynolds number become really high, this term becomes 0, and this is basically just function already. That is mathematical interpretation to the physics. I want you to think about the physics. Okay, and you have, let me give you until next week, because I really want you to think hard about this. This will make you really good fluid dynamicist, right? If you think about this. Yeah, why, when the news becomes so high, the F does not depend on the news number anymore, just epsilon over D. Okay, it's weird, right? But there is a physical interpretation for this. And to help you, give you a hint, to get a free quiz, think about what is the news number? What is this guy?
The
And
Reynolds
what is
number,
it?
the V is the velocity, correct?
Yes, the V is the velocity, the V
So
is the ampere.
So if it's so high, the velocity, it's kind of like skipping over the roughness a little bit, right?
So you guys try to think that the roughness does not matter. The roughness does matter. All those are function of epsilon over D. So the roughness is a big deal. Actually, the roughness is the only deal when the news become high. The question is why the other guys in the news number does not matter. But the wall is always important. It has been important at the beginning and it's important at the end. The only place where the wall is not important is here, actually. It's the other extreme. When the flow is so slow, the news number is so high, then the wall does not matter. Whether you are smooth or rough, it's one friction equation. But when you are very fast, the only thing that matters is the wall. The fluid doesn't matter. You lose your dependency on the news number, but you only depend on epsilon over D. All right, so think about it, huh? And if you have the answer, just email it to me, salam@okstate.edu, and then I will mark you as a free quiz. So that will be, so everyone will get 2 free quizzes at the end of the year. You will get 3 free quizzes at the end of the year if you answer this for me right. Okay, good. So this equation is called the Coulbrook function. And this equation represents those curves, right? And it's pretty accurate. But one bad thing about it, what is it? There is F here and there's F there. So, I mean, if you want to use this in your program, you have to iterate, kind of. You have to assume F so that you can get F, right? So we'll stop here for a 15 minutes break and we'll start again at 6:03.
Hi. Question for you on that. Kind of recall the lecture, the discussion that we had. Is there a possibility of the fluid that's touching the surface being turbulent on the outside and the fluid in the middle being smooth?
I cannot imagine that because the way the instability grows is basically grow everywhere. Everything will be. Everywhere will be turbulent, but I mean the turbulence start at the wall, but it catch up very quickly.
Okay.
If you remember, like, did we talk about the boundary layer?
Mm-hmm.
So I mean, the turbulence start at the wall, but very quickly that entrance length will basically will be just a short distance, and then the rest of the pipe will become turbid.
Okay.
All right. I think we should start. So, people online, can you confirm you can hear me? Yes. Thank you. All right. So we said the pressure drop in a pipe is simple formula, huh? And it's basically this if you want to calculate temperature. So FL over D half rho V squared. The unit is Pascal. Or if you divide over rho and you add a G there, so become V squared over 2G, that become the head loss. Same FL over D V squared over 2G. And we said we're going to get the F from this Moody chart. And Moody chart is amazing, a lot of physics into it. And you get free quiz if you email me why if the use number become high, it become not important when it comes to the F. The F does not depend on the use number anymore. So just send me an email explaining why. And we said that this Moody chart can be expressed by this implicit formula. Implicit because it has F here and F here. That's not convenient. There are formulas that are explicit, but less accurate than the Coolbrook formula. Okay, the formula that are explicit Some of them is called like Swami and Jane, that's famous one. And there's also one called Haaland that I'm gonna post it for you. So they are very simple formula. You just give them the Reynolds number and epsilon over D. And so it's like really as if you are saying, this is my Reynolds and I am on this curve because my epsilon over D. So epsilon over D, epsilon is coming from the material. What is the material? Concrete, glass, that give you an epsilon, and D is the diameter of the pipe. Then you come here and you hit the curve at this point, and then you go and read, what is my F? That's how we do it, right? There is implicit formula, which is this one, and there are explicit that are less accurate, but it's super easy to use, especially in the exam on paper. If you don't want to use the chart, of course you can use the chart too, but you just have to have a really good eye. This particular curve, the last one, is for a smooth pipe. So PVC pipe, glass pipe, things that are super smooth, we just use this formula, right? 0.316 over Reynolds to power 14, and it's also called, this formula is called the Clausius formula. So in my graduate course, so in my graduate course, I teach multi-phase flow this semester for graduate students. So we also calculate pressure drop, but guess what is the pressure drop they are calculating? They are calculating it for bubbly flow, for example, or like slug flow. So they calculate it for two-phase flow, which make it a little bit more complicated. So the pipe is not just water, but it's crude oil and natural gas together. What's the pressure drop? But in our undergraduate course over here, let's stick to single phase flow, right? Just one fluid going into the pipe. So this can also, it's available in this Coolbrook function. So this function, you give it what? What's the input? You see that? It's too small for you. Reynolds and epsilon, right? And by epsilon, of course, you mean epsilon over D. And so based on those two numbers, the mentioned number, he calculate the F. Right? And you can see he's basically saying he's trying to figure out if the flow is he's trying to check that it's really, he's trying to make it dummy proof. And so he's the epsilon and the F, and you can see the formula over here. So you see the 3.7, and he's iterating to come up with the F. So we can use this later on in our, not next week. Next week, there's no homework on this. The homework is just to do the heat exchanger again. Okay, but basically there are codes to calculate this, whether it's implicit or explicit. All right, so we will figure the F, right? And this is the table for the epsilon in feet and in millimeters, depending on the material and the manufacturing technique, because even if it's the same material, even if it's same material, but the way that you made the material can make the roughness different. Okay. You can see how the plastic or glass epsilon is basically 0. So that is the lowest curve. That's the curve with the smoothest curve at the end. And that's why this formula does not have epsilon over D. It's just like function of the Reynolds number, because the epsilon over D is 0 on it, right? Okay, so this is what we're gonna do for a big long pipe. F L over D, V square over 2G, and we get the F from this chart. Now, what about all those valves and elbow and bend and all those, we call those minor loss, because as compared to the long pipe, they will be, like, so the major loss will be 10 meters, and then you have 1 meter of minor loss, for example. But in some network, the minor loss could really not be minor anymore. It could be actually more than the major loss. Think about like sprinkler. Look at all those sprinklers on top of our head, you know, and now imagine how many elbows they have compared to the straight pipe. And the pressure drop in the sprinkler itself. So that network, the minor loss could be, you know, really significant compared to the major loss. So if you remember, the way we calculate those minor loss is by this guy. What do we call this guy? So instead of, what did we have here? We used to have FL over D for a pipe. Now the FL over D is replaced by KL. What's the name of that KL? Does anyone remember? Loss coefficient, called loss coefficient. So that loss coefficient is basically function of the geometry and sometimes function of the opening and closing of that geometry. If that's a valve, you will find a table that basically tell you K as function of quarter open, half open, fully open, and he will tell you what's the K value for it. Okay. And so later when we do a heat pump, the water go into the heat pump, right? And what's in the heat pump? It's a big heat pump condenser. So when the water go into this unit, the water is coming from the ground by a pump and then go to that, it basically change with the refrigerant, right? In some kind of a heat. So this one is air to water heat exchanger. Not air water, air refrigerant heat exchanger. So this would be an air source heat pump. So this unit will sit outside your house. Refrigerant is coming into the pipes and air is being pulled around the pipes with the help of the fan sitting over here. In a ground source heat pump, the refrigerant will be coming and then the water from the ground will be on the other side. But at any rate, what happened is that there is network of pipes and elbows and turns that the water will go through. Okay, so all this unit, with all its pipe and network, all this can be represented as a symbol K. Like I will give you a homework problem which would say that heat exchange, that the whole external unit can be represented by, you know, a minor loss K equal, I guess, 400, not by 2 or 3, no, it's going to be like K is equal 400 multiplied by V squared over 2G in the pipe, V squared in the pipe coming to it. And then you multiply by K equal 400, that's your pressure drop in this list. Okay. So that K can be really a powerful tool, right? And sometimes those fittings, rather than giving you K for them, they give you what? They give you lengths. So they will tell you that valve, being half open or like quarter open or 3/4 open, that valve, it will be as if you extended his pipe, the pipe coming toward him by 2 meters, for example. That is his equivalent length. And if that is the case, you just tell yourself, how long is my pipe in the 10 meter? Let's add 1 more or 2 more meters because of that valve, and 1 more meter because of the elbow, and one. So all the fitting can be either a K or an equivalent length, and you just add them to the pipe, and you treat them as a pipe, and you basically say, here's my F for all those pipes, all the original pipe and the extension, all right? And in this part, I'm saying which V, because sometime, not here, but in some like this, you are wondering like which V? Is it V inlet or V outlet? If he gave me K for that sudden expansion, Sorry, this is sudden contraction. If you give me k equal 0.7 or like 2, or should I multiply by v1 or v2? The velocity before or the velocity after? Which one? The answer is follow the recipe. The table that this key came from, they will give you in the key. You cannot, this is not about guessing. It's not about physics. This is about the way they made this chart. So you just follow exactly if you're gonna use their key value, you better use the recipe, right? So you could find another chart that's based on that V instead of that V, and it's totally correct. But of course, the key number will be different because it's based on different velocity. Yes. So notice how this key now is function of area 2 over area 1. So if area 2, the small area over area 1 is 1, the key is 0. Why? Because you are saying same area. Area 2 is the same as area 1. So it's a straight pipe. So what's my key? It's going to go to 0, right? This actually is a really good point to make, that sometimes, you know, when you have a formula or something, driving it to the extreme can really help you to see if it's a sound model or not. Huh? Just like, what's your name again? Michael, right? What's your name? Charlie? Charlie said, you know, like when we're asking like why the unit number wouldn't matter. And he said, because when this go to infinity, then it will drop out. See, this is also a way for you to check, is this formula correct? And you can see what happened at the extreme case. What happened at the extreme case? Unit number becomes so big, that term will go to 0, and the f will just be function of epsilon over d, which is actually happening. Right? So then, yes, this formula is correct. So you can learn a lot, huh, by just taking everything to the extreme case, kind of like best case scenario and worst case scenario, and see if it makes sense or not. Okay. For example, look at here. This is the sudden expansion. Again, it's function of a velocity. Which one? Listen to the recipe. So here he is using V1, then we use V1. Here he used V2. Let's use V2. Right? So I could understand easily, huh, why if you have sudden contraction, you have a pressure drop. Because I mean, you are annoying me, you're giving me smaller area. Yeah, I'm gonna drop my pressure. It goes through this tiny hole. But why going to sudden expansion also have a pressure drop? Why is that? That sounds like, I mean, you're giving me a break. So you're moving me from a small house to a big house. And still I will feel annoyed and I have to pay out of my pump. Why is that? Can you explain why there's a pressure drop when you go from small pipe to bigger pipe? You have what? Yes, exactly right. What's your name? Steve is saying, because look at this corner. What happened at that corner? Can we imagine? It must be a circulation. I mean, let's not call it turbulent. Even if this is nice and laminar, there will be a circulation bubble. Huh? There will be a place where the fluid is rotating. And if things are rotating, it costs joules. And who's paying for those joules? Huh? The pressure drop that will happen. Okay. So this is actually really nice. So although Bernoulli will tell you that you go from high velocity to small velocity, going from high velocity to small velocity, why the velocity here is smaller? Because the area is bigger, and because AV equal AV. this area 1 times V1 equal area 2 times V2. Yes, the velocity will drop. And the pressure P1 will actually go to higher B2, but not as high as it should be. How high it should be? Bernoulli will tell you P1 plus V1 squared, P1 plus half rho V1 squared should be equal to B2 plus half rho V2 squared. So you drop my V2 10 times. No, it's too much. You drop my V2 by 2, then V2 squared will drop by 4, and I'm expecting my pressure to recover this much. The pressure will recover, yes, definitely V2 is bigger than V1, but you will not go to the ideal. You will go to a smaller, a little bit smaller than the ideal. Why? What is that? That is KL half rho V1 squared. Okay, that part that you lost is because of this circulation bubble here and circulation bubble over here. Okay, so anytime there are certain expansion visualization. Maybe video. No. I don't see the video, but maybe images. Yeah, so those guys, you can see the streamline, huh? You can see also over here how the flows are going straight and there are all those circulation. Right? So those, of course, see how they're trying to minimize this by taking the flow into, rather than sudden expansion, they are taking into guided expansion. And that's why you will see the people in the HVAC industry, whenever they want to go from small duct to big duct, they spend the money and the effort to go with a cone, because they don't want to go like this, because they know they're going to pay for that circulation bubble for the rest of the project. As long as this duct is there, that circulation bubble will keep running, that blower will keep paying for it, right? So they try to go to a guided expansion, right? So it's this guy that we are paying for. And so eliminating it is really a good deal. And that's also why if you go to big wind tunnel, you'll find out they don't have 90-degree cross-section area. They try to basically have it like chamfer the corner, because they don't want to have eddies sitting there and disturbing the test section. Good. All right. So even elbow also, it's the same idea. When you have an elbow like this, you think, you know, that's guided flow. Like, what are you talking about? Why there's energy loss? But you don't see that the flow will separate, and that separation will increase with the radius of curvature, right? And so there is K, there is loss coefficient, that's function of like, are you turning 90 degree on me? Or are you taking it slower so that I can help the turning basically? And in big corner, they can reduce the pressure drop a lot by having guided veins inside. So the flow wouldn't basically separate. So they can take him slowly and guided. So there are tables and charts for all those minor losses. You can find something like this. And some are more complicated than the other. And you just assemble all those K, and then it's not just, then the minor loss becomes sigma KL E square over 2G, right? And you add all those K for the, and this is the one that I was telling you about when they try to go from one section to the other, even say from round to rectangle, you have to slowly do that transition so that the flow does not really make you pay for all the separation and circulation. But also this raises an important question. If I have a circular duct, I know how to get the diameter, I know how to get the Reynolds. I can go ahead and use the Moody chart. And the Moody chart have epsilon over D, right? So everything is perfect. But what if I have a rectangular duct or square duct? Because they are easy, you can fit them under on top of the false ceiling easier when they are rectangular than they are circular. You can hold them easier too. So what if I have a rectangular duct? How do I get my Reynolds number? How could I get my epsilon over D? And this will introduce the concept of hydraulic diameter. So that is really, really good. And it really worked. And I tried this myself, actually, even in my PhD, for like really weird configuration. We wanted to calculate things for an annular flow. It's like this. What's annular flow? Flow between big pipe and a small pipe. Okay. So even for this, the concept of hydraulic diameter worked perfectly. So basically, the hydraulic diameter is a way to express all those weird cross-section area with a diameter, equivalent diameter, because the Moody chart need the diameter in the Reynolds number. The epsilon over D need the diameter in the chart. So how do we come up with that diameter? 4 times the area, the cross-section area. The cross-section area is easy. That's this guy times this guy, A times B. Even here it's easy. What is the cross-section area? Pi over 4D squared minus pi over 4D squared. Big area minus small area. That is your cross-section area. Now that P is weird because out of all the symbol in the world, they picked P because we are calculating pressure drop. So you may think that's the pressure. No, it's not. It is the weighted perimeter. Okay. So what is perimeter? Well, the perimeter, of course, is this. Okay. And over here, what would be the perimeter? It's that diameter plus this diameter. It's basically the wall that you are touching, the length of the wall. But weighted mean that the place where the water, not the water, the fluid is touching. I mean, wouldn't the fluid touch everywhere? No, not necessarily. For example, if there's water flow and it's going into rectangular duct and he does not fill the whole channel, it's only halfway, then the weighted perimeter would be only the part that he will touch. Okay. Anyway, if you work the number in a pipe and you say, what is the area of a pipe? Like this pipe, it's pi over 4D squared. What's the weighted perimeter of a pipe? It's pi D. You will see the pi cancel with the pi and the 4 cancel with the 4 and the D squared cancel with one of the D. And then you'll end up with, for a pipe, this concept become just the diameter, which works. Again, that's the extreme scenario. Then if for all the other guys, I mean, you can work your number, or you can just like in a table like this, just trust them. The diameter is D2 minus D1. And for rectangular, it's 2AB over A plus B. And if you don't believe them, just do the 4 cross-section area over the weight perimeter, and you will see it works. Okay, so that is the DH. And I can go ahead now and go to the Moody chart, right? And use that diameter, the D minus D for annular flow and the 2AB over A plus B for the rectangular duct, and calculate the diameter. How about the velocity? Q over area. What area? The whole area in the Q, right? So by the way, did you know rho V is actually m dot per unit area? So rather than calculating if he give you the m dot, rather than go and calculating the velocity, you can just go ahead and calculate m dot over the area, and that become rho V. Yes. So rho V is a kind of the mass flux. It's the kilogram per second per meter square. So don't have to calculate the velocity if he does not want you to calculate the velocity. All you need is the Reynolds number. And I will come over here and basically say roughness from the material he's giving me over the diameter of the pipe, the hydraulic diameter of the duct. and figure out which one I am and just follow the curve to the right, Reynolds number and read my F. Good. Now, the only trick is for those weird geometry is the laminar part. The laminar part should be 64 over the Reynolds for a pipe, right? That's the laminar part. If the flow is laminar, we just use 64 over the Reynolds, not for those weird geometry. For all those weird geometry, we don't use 64 over the Reynolds. What should we use then? 71 over the Reynolds, 96 over the Reynolds, all those weird numbers, depending on the geometry. So they will give you T1 over D2, and based on it, you will use those numbers. Okay? So for example, rectangular duct, if A over B is so small compared to B, so it's like a slit. Really, the number become, you see, so high, 89. And only when that ratio start to build into a square, you see yourself are basically getting smaller, right? So that equation for laminar flow tell you which number you should use for the laminar part. That constant C, it's written in the way of like F multiplied by Reynolds and Reynolds H. What H stands for? Hydraulic diameter. It's telling you that C is not 64 over the unit. It's those numbers depending on the geometry. Does this make sense? Yeah. Very good. So the problem in this is basically in pipe flow. Calculating the pressure for pipe that you know and flow rate that you know, that's easy. That's using the Moody chart and the formula. Delta P is Fn over D, V square over 2G for HL. It's when, and that's basically type 1. Just calculate the pressure. Type 2 and type 3, those are basically when he asks for, I have this pipe and I have that pressure. What flow rate do I have? Okay. And in our course, when we are designing the system, we don't have a pipe. We are trying to make a pipe, right? So we basically know a flow rate, and we know that the only pump that we have is like this much, for example. This is the design consideration. Like in the market, we don't have anything bigger than this head. So what diameter you should use? I mean, it's the same formula. It's just like what is given and what is required. So if the required is a pressure, easy. If the required is flow rate or diameter, a little bit tricky. Why tricky? What's the big deal? I mean, look at this formula and tell me, what if he actually know the delta P and the flow rate, but you don't know the diameter? Why this has become hard then? I mean, can I just calculate the diameter? You said you have 10, like let's use the head. You have 10 meter and the flow rate is 10 gallons per minute, and you just want me to calculate the diameter. Can I just pull the diameter out of this formula? No, I can't, because the F, I don't know the F. Why I don't know the F? Because the F is function of the Reynolds, which is function of the diameter, and F is also function of the diameter. So that requires trial and error, because the way the chart is set, right? There are charts in the industry for engineers that are basically don't have the time to iterate. So the charts are done in a way that it gives you exactly what you want. I'm going to show you some of those, right? That you basically give you what you want immediately without iterating. But the chart that's done like this is only for water, for example, not only for a certain pipe material. They will tell you this is for stainless steel pipe schedule 40. So when they take out the material, epsilon, and or they even take out the fluid, there is no rho over mu, because it's only for water. We know the rho, we know the mu. Then the chart become easy, and it just become like, let's go find the amplitude, right? But I'm gonna actually ask you, I'm gonna show you those chart, and then in the next homework, I'm gonna ask you to make one of those charts yourself so that you can see it's super easy to come up with a kind of a design handout for your company, right? Once you fix bunch of parameter, then the equation just becomes simple relation between head and the diameter. So, so basically, it's just like the iteration over the F. That's what make type 2 and type 3 a big deal. Okay. So here's an example of type 1. You are given all the geometry, length, and the diameter somewhere here. Yeah, 0.75 inch. That's the diameter throughout. And copper pipe, drawn tubing, so you can go to the material and find out what their epsilon is. And the flow rate is given. You know the flow rate and you know the area, then you know what? The velocity. Because Q is AV. Q is AV. Right? And we have basically all those elbows. 1, 2, 3, 4 elbows and one wide open globe valve, which will still, even if it's wide open, it will still have some loss. And the faucet itself, which has a KL equal to based on the exit velocity, right? And he said, we'll determine the pressure at 0.1. Basically, what pressure need to drive that flow rate? What pressure need to be here so that you can deliver that flow? What's the pressure here at the exit, by the way? Anyone?
0.
No, 0 gauge, correct. So absolutely, from absolute point of view, it's P ambient. So from absolute point of view, it's P ambient. If we're going to stick to P ambient, then we're going to calculate B1 on top of B ambient, right? If we're going to say that P2 is 0, then what we mean is P2G is 0, right? And then we can calculate B1 gauge above B ambient. So the question is, can B2 be anything less than B ambient? I mean, this is the pressure outside, immediately outside, once we leave. Can that pressure be anything outside different than B ambient?
No, shouldn't be able to.
So the answer is online, no, it shouldn't. And the answer here in the class, maybe it can be lower. It cannot be lower, so it can be higher. Can it be higher? So here, this will blow your mind. So the question is, the answer here is like, it cannot be lower because like, how could you leave? So here's what's going to blow up your mind. So if this was supersonic flow, supersonic exit, so we are not talking about water coming from a faucet, but we are talking about maybe a vent from the International Space Station, or maybe a gas leak from a tank or something, pressurized tank, and the flow is leaving at supersonic speed. If the flow is leaving at supersonic speed, the pressure at the exit could be higher or lower than B ambient. It can be higher and it can be lower than B ambient. And then, of course, once the flow, that's immediately at the exit. Once he leaves, like the first millimeter he take out, he will realize like, what? Look at that pressure outside. I mean, so supersonic flow leave blindly compared to the pressure. He have no idea what is the pressure outside. That's what it means to leave supersonic. you are moving faster than the pressure wave. So you are just rushing out, and then, but the flow is around you. I mean, once you step outside, the pressure around you will like, wait a minute, you are lower than pressure, lower than our pressure. We are ambient, and you are like maybe 0.5 be ambient, or like you are lower than us, and they pushing you. And that's why you would have, you look at choked gas jets.
Is it because it's leaving so fast, it's pushing the air away?
It's leaving so fast, it is blind. He cannot really sense the pressure. He does not know what's going on outside. This happened. So the flow on the outside say, you are lower than us, and they push on him. And the air get contracted, and then they push so much, they make him even higher than them, higher than the ambient. And he would like, and he explode, and he explode too much. And then he become less than the ambient, and then tuck, 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 tuck. And that's why you would see, you say diamond shock. You will see this, and you will see this, and you will see this, like in those airplane when they fly, and like in test stand when we do jet engines, so like for the Air Force, you see this, what's going on. He is leaving with pressure that is lower than the ambient. And then the pressure here catch up and say, wait a minute, you're lower, and they push too much. And of course, this process does not continue forever, maybe continue 5, 6 diamonds. And then it disappeared because of that process is not reversible. So entropy build up and it eats your pressure. And so by the time you finish, like 6 or 7 diamonds, there is nothing to continue that trend.
You can see it nice in the picture below, it like fades away. Like it's a clear diamond, then it fades away.
Say that again.
The picture you're hovering over, you can see it. It looks like a nice crisp diamond and then fades
Yes.
into a fuzzy one.
Yes, and I saw that myself when I was a postdoc in the Air Force Supersonic Wind Tunnel. I was setting my optics and I wanted to align the laser with the wind tunnel. And so I told my technician, just blow some air for me so I can see where the jet is. And the air was supersonic and the laser was illuminating. And I saw those diamond shape up close and they are so beautiful. I mean, mine was so tiny too. The whole thing was 1 millimeter. So like I had looks those tiny, cute 1 millimeter diamonds sitting above each other. But again, they just like die in like 4 or 5. So this is if you are going supersonic. What is the speed of sound in room temperature? 340 meters per second, right? 340 meters per second. There is no way this guy is going to be. And by the way, the speed of sound in air is different from water. Which one is higher? Water. The speed of sound of water is way higher. Talking about 1300 meters per second. So you need to be like 2000 or something. You need to be supersonic in water. All right? So as long as the flow is subsonic, less than the speed of sound, there is no way that pressure can be different from the ambient where he's coming out. Because the ambient will catch up immediately. He does not have the luxury of like, and leave without looking behind. The pressure wave will travel in him and adjust him before he even leaves. So subsonic jets, which most liquids, because it takes huge power to actually accelerate this. Even gas jet is actually, it takes a lot of power to make it supersonic, right? So needless to say, when I was working for the Air Force, our supersonic wind tunnel, it took 20 megawatts to run. 17 kind of megawatt. And we couldn't run before 5 p.m. We have to wait until people shut down and go home. And we keep calling the control room. Do we have 20 megawatt? Do we have 20 megawatt? And when like my 5:30 or something, they say yes. Then we turn the compression station and we run our wind tunnel basically. And we run until midnight when the technicians say, this is crazy, you have to go home. So we run from like 6 all the way to midnight. because you get like, you don't have that many test nights where you have all this power just for your wind tunnel, because there's so many test cells and everyone need his day of the week to run their tests. So you get like, say, 1 night per week if you're lucky. Right? So end of the story. Subsonic jet, he will have to be ambient. You will have to adjust to the pressure outside. Only supersonic for a very short distance, and you see that choke trail that adjust him and get him to be ambient within 5 or 6 diameters. Okay, very good. So in order to calculate that pressure on top of that pressure, or the difference, it's basically what? It's basically the friction pressure drop. It's FL over D, V square over 2G, plus sigma K, all the Ks, right? So he said, now calculated if all the losses are neglected and the only losses included are major loss, and then the last part is like all losses are included. So he wants you to repeat this when HL is 0 and when HL is major, and the third one is when HL is major and minor. Okay, so this is applying Bernoulli between 1 and 2. All right, so between 1 and 2, what do you get? You get the head that you are rising up to, right? So if the water is delivered here and you need to go up to 20 feet because you are delivering to the 2nd floor, and you have to go through all this, then the pressure need also to pay not just for the friction rho GHL, but you're also paying for the static pressure, for the elevation, rho G delta Z, right? And notice that it does not matter where is Z equals 0. You said Z equals 0 here, or you can set Z0 equal here, and this become minus. At the end of the day, the pressure will pay for the pressure difference, for the static difference. Yes? So then that makes sense then why they would say that the H loss, which is all the friction and the elbow, they equate it to a head. Because as far as the equation is concerned, the pressure is paying for rho G times certain meter. Whether those meters are static or dynamic, static or friction, and then the pressure here, which is coming from the pump, need to say 10 meters of elevation plus 3 meters of friction. So it makes sense, we call it head loss. I mean, think of it as basically, if it wasn't for this guy, we would have gone 13 feet up. But we have a head loss of 3 meters because of all the friction that's eating the elevation from us. Like we are sharing resources. Rather than all our energy is being paid for going up, we have to share with the friction. Yes? Okay. And notice how the V1 and V2, if it's the same area, then it will be the same velocity. And those two guys will cancel out. But if this diameter here is 0.75 inch and this diameter is 0.5 inch, then the smaller diameter will have higher velocity, right? And so the pressure will pay for the difference, right? The pressure will have to pay for the difference. So now, in this case, where the velocity here is considered as here, like if let's read this problem and calculate the pressure difference that it takes. Well, V1 here is almost 0. Why? Because the area is almost infinity. But then V2 is small. Sorry, area 2 is small and V2 will be big. So this would be, you have to pay for this, right? So whenever you are pulling water from a big tank and you are delivering it at the exit into a pipe, you pay for that exit. So this actually is called the exit velocity loss, or like the exit loss. And you basically Imagine if this one is 0, then you are paying for all this. You're paying for the half rho V2 squared. So they will give you this with a K that's equal 1. Basically, all the dynamic pressure is lost at the exit. K will be 1 equal at here. Yes? So you can see, then he basically just like put the velocity over here. And so it's the elevation plus half rho V2 squared minus V1 squared. And if V1 is 0, then you are basically losing all this. And measure loss. Right? And he's getting the measure loss from the Moody chart. Right? And it's important to calculate all the lenses. So you can see how there is like 15 plus 10 plus 5 plus 10 plus 10 plus 10. Yes. And for the minor loss, you have to add sigma KL. And here are all the Ks. Valve and elbow and faucet. All right. Questions? So now in type 2, when we don't know the flow rate, determine the flow rate through the pipe and the turbine. So again, what's the problem? When you write this equation, your problem is you don't know the F. Right? Actually, this problem was made artificially easy, because he said assume the F is 0.02. But if he didn't say that, and we are really solving the problem for real, and we are saying we have 1 feet diameter, and the lens is 300 feet long, okay, and the pressure driving it is like basically coming from that elevation head, and he said calculate the flow rate. We will have to do what? We will have to assume F, and once we assume F, then this equation will have only one unknown, which would be the velocity. Then you will be able to calculate the velocity from it, and then you check again. So you assume the velocity, calculate, or you assume the F, I guess. You assume the F, and then you calculate the flow rate, and then you go back again and check on the F. Right? So in this particular problem, he said minor losses are negligible. So like this elbow and whatever is really tiny. And also here is one difficult part in it. So if the flow is just leaving from here and here, from the tank all the way to the exit, the Bernoulli equation would say the stuff at the beginning, energy at the beginning, which is pressure and velocity and elevation, equal to the flow at the exit plus the loss. Okay? But because there is a turbine over here that extracts power, that turbine can also be expressed just like the pipe loss with meter. So you can express the turbine as 4 meters of head or whatever the turbine extracts. Not only turbine can be expressed like this, but also the pump can be expressed like this. If there was a pump sitting over here, then we will write HL over, sorry, H pump. It will be considered as part of the input. Energy available at the input plus the pump equal energy at the exit plus the turbine plus the loss. Okay. The project 6 actually has this hydropower storage system. What is a hydropower storage system? I'm still writing it, but you can have a peek. Week review here, project 6. And it's basically this, that you are taking water from a low reservoir. If you have a lot of energy and you don't know what to do with it because the wind turbine is running and people are sleeping, they are not using the electricity, and you have a pump that take the electricity and take the water up, set it on the top. And then at night, I mean, you keep doing this and pump the water up. And then in the morning, when people start running their coffee maker and turning on the light and or even go to work and HVAC start working, and the wind energy is not available or just the load is big, then the water flow the other way and this to become a turbine. And the turbine basically get energy and you benefit from the energy. And as a matter of fact, PSO over here that run the grid for us, that you get your electric bill from them every month, they actually store the energy like this. They don't have it here in Oklahoma, but their grid is not just in Oklahoma. They run the grid in a bunch of states. I think all the way to Ohio, something. Yeah, and so they had a energy storage station, and they do this. So the way to design something like this or to run the calculation is basically similar to this, huh? Except that this is running in the turbine mode, and when we run in the pump mode up, this would be 0, and the pump would be here, right? And you will take it from here going to the other way. And of course, unfortunately, H loss is eating from you in the way down and in the way up. Whether the flow is going into driving a turbine or a pump driving it, you lose H losses everywhere, back and forth, back and forth. Okay? So what is important here is to remember that H turbine can be expressed in meter. H pump can be expressed in meter. So that's not that easy because usually the pump or a turbine is also rated in kilowatt or megawatt. They are telling you, you are designing a 50 kilowatt or 2 megawatt pumping storage system. So how you can turn this power, whether in horsepower or megawatt or kilowatt or whatever, how do you turn this into meter? How? If I have a turbine that's 50 horsepower, and you want me to write the Bernoulli equation in that form, how many meter is the head of the turbine? How do I come up with that number? And actually, let's do it for a pump first, huh? Because the pump would be easier to imagine. So if H pump, not H pump, the head of the pump is like 10 meters. What is the power of the pump? Help. So I remember when we did the Rankine cycle, we used to say the power of the pump was m dot delta H to start with, right? Delta H. And that delta H was in what unit? The m dot was kilogram per second, and the delta H was kilojoule per kilogram. So I need my energy in kilojoule per kilogram. So I can multiply by m dot. So if only we can express that head pump in kilojoule per kilogram. So how do we do this? So it's m dot multiplied by GH. That's how it works. So G, the 9.81, the gravity, 9.81 meters square per second, multiplied by the head of the pump, that is actually joule per kilogram. Okay. And also that H pump can be expressed as what? As rho. So the H pump is delta B over rho G, right? The H, the head in Bernoulli can be expressed as, because the delta B is rho GH. So the H is delta B divided by rho G. So cancel the G with the G. And what do you get at the end? You get that it's V dot time delta B. Rho is the density multiplied by the gravity. So why? Because the delta P is rho GH. So H is delta B over rho G. So the two equations that I want you to remember, or the two facts, that is this, that you can calculate the required head of a pump or a turbine by V dot, the flow rate, time delta P, or M dot GHP. Okay, and so this coming from the fact that this head pump is really rho, not the H pump, the delta P of the pump is the head of the pump multiplied by rho GH, rho G. So density times G times HP. Actually, I always memorize it since I was undergrad as this, rho GH. And you probably remember this too, rho GH. So the delta B on the pump is rho GH. Okay. So you can get the head from the power. You can get the head from the power by basically saying that it's M dot GHP. Okay, and that's what you see over here. See, he got this weird pressure, it's not really pressure, it's the head. Sorry, it's a power. So this power, dividing it over, what is this gamma? Specific weight. What's specific weight? Rho G. So this is rho G flow rate Q. So he's basically saying the rho G, or basically M dot GH is the power. So you can get the H from power over M dot G. Okay, this I'm gonna email you this, or like maybe post it so that you would see what we wrote. So the head is this. So this equation that basically say this, the relation, what is the relation between the head and the power? And the relation is the head is the power divided over M dot G. This is M dot G. Why? Because this gamma is rho G. And this is the flow rate. So it's M dot G. Yes? So this is what need to be etched in stone. That the power is M dot GHP. The head of the pump times G, that's joule per kilogram. And you are multiplying it by kilogram per second. And you can get your horsepower. Okay? So he can do this for the turbine and he can do this for the pump. And you can turn the turbine into a head of 5 meters, or you can turn a pump head into someone tell you this pump have a 10-meter head and it delivered that flow rate, then you immediately know the horsepower. Yes. Okay. So I'm going to say that valid for both turbines and pumps as well. Both of them work like this. Okay. Again, I'm going to post this for you. I'm going to call it class notes or something. So when he's trying to figure out again what is the velocity that is running in a system like this. All right. And so he's applying Bernoulli, and so he's saying Z1 is the losses head plus the turbine head. Losses head is F L over dV square over 2G. He does not know the V. That's fine. That's what we are solving for. And the head of the turbine is coming from its power, 50 horsepower, divided by its M dot G. This is M dot G, right? And the M dot is simply rho, which is part of the gamma, time the flow rate. What's the flow rate? Area time velocity. So then he figured out that the head of the turbine is also function of the velocity. So this make this equation, although you have like 90 feet available for your pipe and the turbine, and that's what we're gonna do in this design course, right? Sorry, in this design project where we will project 6, where we're gonna basically have a certain head for us. We will basically say that head is gonna be losses plus that turbine. And then when we run the pump would basically try to spend energy on what? Losses plus the head, right? In the way filling, we pay losses. In the way back, we pay losses. Everywhere we pay losses, back and forth. So then this equation, the 90 feet is divided into losses and head. And notice how the exit, you see that exit, that V2 square over 2G, it's here. It's basically part of the losses. I mean, you could actually, in many places, they would, when they count the losses, they would say, I have the pipe loss, FL over dV square plus 2G plus 1. That's also loss for me, right? So you consider that exit as part of the FL over D. It's a K. It's a K equal 1 for the exit flow. Okay. All right. And so he iterate to one unknown here. He basically solved for it for V. But what would make this problem even more complicated, which is the case in our design project number 6, is that we are not going to assume F equal 0.02. Or not assume, but I mean, we don't know the F. So we will have to, on top of that iteration, there's another iteration that say, what F are you using? Is it correct? No, go back, fix it, come again, right? So when you calculate the velocity, you need to revisit that F and tell yourself, is it 3.02 or should I have used 0.01? You got it? So this problem is almost half of the second 6 project. In the way, this is in the way down, and then you solve it again in the way up. Questions? All right, so let's take a 5 minutes break, restroom break, and we'll start at 7:15. So 5 minutes break. All right, so let's start again. So we said the first type of those problem, geometry is known, flow rate is known. You just want the pressure drop. Solution, delta B is FL over D half rho V squared. Easy breezy. Only the difficulty is just getting the F from the Moody chart. That's okay. Second part is second type of the problem is that if you don't know the flow rate or you don't know the velocity, because if you know the flow rate, you know the velocity. And so that was like gonna be something like this. And you're trying to figure out how much is the power. Sorry, how much is the flow rate going on and off. And so is that you really have to iterate, not just because the equation is second order in V and you cannot get the V out. I mean, that's not the only reason that you're iterating. You're also gonna iterate because the F, leaving it as 0.02 or whatever the value that you assumed is not good. You have to check on it. You have to assume an F, calculate V, from that calculate an F and check if your assumption is right or wrong. Okay. And we saw that part about like how does a turbine that is rated at 25 horsepower or 50 megawatt or whatever the energy, the power is, how you can turn it into a meter in the Bernoulli equation. And it was through this equation. The equation that say the power of a pump or the power of a turbine is simply m dot GH, where H is the head of that turbine or the head of that pump. Right? And we wrote this in this equation like this, which translates into this. All right. So the third kind is if the diameter is not known. And so you are really designing the pipe, right? And that probably is really what will happen in the sixth project, because we will say we know that head of the mountain, that's what's available for us. We are trying to buy this pump / turbine combination, and we are trying to figure out what is the piping system for it. How large should be the pipe? So either way, whether you know the velocity or whether you know the flow rate or you know the diameter, type 2 or type 3, it's the same problem. What's the problem? I don't know the F because I don't know the V. So the V will be unknown. The V will be unknown whether I don't know the diameter or I don't know the Q. Either case, I don't know the V. So the equation will end up looking the same. The equation will still look the same. That basically you have a, see here he's writing the velocity as q over d squared. So it's the same equation, huh? And you have no idea what the f is. And also you have no idea what the velocity is, which is q over d squared, right? So what will happen if you look here, you will basically have to assume and calculate. Look at this. You basically find out and eventually an equation between the diameter and the f, right? And so he's basically saying assume the diameter. Once you assume the diameter, then you calculate the f, and from the f solve the diameter and go on and forth until basically the number that you assume is the number that you calculate. All right? Question? Huh? So the Bernoulli equation by itself is a piece of cake, right? Energy in, what's the energy? Pressure plus half rho v squared plus rho gz equal energy out plus the losses. If there was a turbine in this pipeline, we will put it over here. If there was a pump in this pipeline, we will put the pump here. The pump is considered part of the energy in. And the turbine is considered as part of the energy out. It extracts energy out from us, right? So just try to remember where you put the H turbine and where you put the H pump. Right? And see, this is the Coulbrook formula, but again, there's explicit formulas. I mean, the reason if we use this formula, then you are iterating for 3 reasons. You are iterating because you don't know the Reynolds number, you cannot use the Moody chart. And then in the Moody chart, you are iterating because of that the Moody chart itself is, or the Coulbrook formula is implicit. But again, if you use a software like a function like this, then you let them iterate inside. You don't have to worry about it. Or you can use an explicit formula, so you run away from this. Question so far? All right. So next part is, what if we have a bunch of pipes? And this sounds easy, but when we go to the ground source heat pump, that would be really a problem for us. The problem is your eyes will not be able to tell you, are they in parallel or in counter, or like in parallel? Are they in parallel or in series? And which one is in parallel and which one in series? Okay, so let's at least understand, once we identify them correctly, what should we do about them? So if the flow in parallel, if the flow in series, that means one delivered to the other, right? And obviously the flow rate here is the same here, is the same here, because they have no way to go. And on a steady state basis, if there is 10 gallons per minute here, it has to be 10 gallons per minute here, it has to be 10 gallons per minute here. And the pressure drop would be this plus this plus this. That's easy too, right? Like if you are gonna have a line that go from Tulsa to Stillwater, then to Oklahoma City, first you wait for the pressure drop from Tulsa to Stillwater, and then from Stillwater to Oklahoma City. You have to add. That's easy. So series is easy, I think. It's the barrel that's confusing, specifically the pressure drop on the barrel. So what's the barrel flow? They all come from one place and they leave to the same place. They come from here, leave there. Okay, they have the same start and the same end. And so if they all start from the same location and they end up at the same location, what's the relation between their pressure drop? It has to be exactly the same. So if this pipe has 10 meter pressure drop on it, this one will also have 10 meters, this guy will also have 10 meters. No matter what's the diameter, what's the length, even if this one go a little bit longer before it come here, if they start at the same place, finish at the same place, because I mean, this is the pressure here 50 and the pressure over there is say 20, then everyone has 30 difference on it, right? Does this make sense? So this would be the part that you will not buy later on, that you like, why have the same pressure drop? And then I'll tell you, they're starting from the same point, finishing at the same point. Why wouldn't they have the same pressure drop? Okay. Yes, very good. So of course the Q total would be this plus this plus this, right? Every one of them has his own Q, but they cannot have different pressure drop, right? Here they have the same Q, but they have different pressure drop across them. So here is this example. This is actually coming from the fluid. All this chapter is coming from the Okishi book, the one that you're supposed to have it in your fluid, your first fluid mechanics course. Now they used to call it engineering science 3233. Now they're calling it MEE 3333. Because basically our mechanical department decided that we are not gonna share the fluid mechanics course with civil and chemical. Like it used to be one course called engineering science, and everyone, chemical, civil, mechanical, they all have the same course, and that different professor from the same, especially in Stillwater. I mean, here on this campus, we only have mechanical, but in Stillwater, they have all the departments. And so then the course is basically open to everyone, civil, mechanical, anyone can take it. But then they decided that we're gonna split and have our own course that say we don't have to study hydraulic channels and like things that are really interesting civil only. We want to care about only things that are related to mechanics. But this is coming from the Okishi book, right? So here is flow between two tanks, okay? And this is a cross section. Like when you do this symbol, what does it mean? You have a cross section, right? So this is basically those 6 channels. The flow is going into those 6 channels between this tank that's under pressure and this tank over here. And he said that he wants to send the flow rate of 30 millimeter cube per second, right? Minor loss are negligible. What minor loss? The inlet, there's losses here associated with the inlet. And depending on the inlet curve, sometimes they design the inlet with a really round entrance. That would be a small loss compared to a sharp entrance. Why? Circulation and eddies and stuff. So you got inlet loss and you got exit loss. Exit loss equal K equal 1. So he said that the minor loss are neglected and he wants to know what pressure here, what pressure should be here in order to be able to drive that 30 millimeter cube per second. Right? And he giving us the density of the fluid. This is specific gravity, not specific weight. So specific weight, gamma is specific weight. What is specific weight? Rho g. SG is specific gravity. What is the specific gravity? Well, specific gravity is specific weight. Specific weight is rho g. Now the specific gravity is, well, anyone? No, try again. Yes, it's rho fluid over rho water. But not any raw water. Raw water at 4 degrees C. Why is that? So that it become rho over 1,000. Because water at room temperature is 998, right? 998. But so that he can divide over 1,000, it's like raw water at 4 degrees C, very chilled water. So, you know, I mean, it's like, we know that he's just want to divide over 1,000, you know. They could have just said rho over 1,000, but no, let's call it specific gravity and let's say it's at raw water at 4 degrees C. So when the systemic gravity is 0.85, obviously the density is 850, right? You just multiply by 1,000. And the viscosity of 0.1 Pascal second. So it's important to remember that the viscosity, just like when you say viscosity, you really mean dynamic viscosity. Okay, and that is the one that is for water, it's like of order of 0.01 Pascal second. There is another kind of viscosity, and it's called, yes, kinematic, yes, kinematic viscosity. And that one is in, it's basically the viscosity or the dynamic viscosity divided by rho. So it's, so this guy, that viscosity, we usually give it the symbol mu. And the kinematic viscosity, we give it the symbol mu, right? And of course, in Greek, I don't know, here is a mu, right? So that is a mu. And the nu, I don't know where it is. Here is a mu, we got it. And probably this is too small for you to see. Let me make it bigger for you. All right. So the mu is the viscosity, and the nu is the kinematic viscosity, and it's viscosity over rho. And for water, it's of order of e to the power -6. Why? Because you are dividing e to -3 over another 1,000, right? More or less. So you get, but it makes them super easy to remember them, because I mean, one of them is 10 to -3, the other one 10 to -6. And the fact that you're dividing over 1,000, so you just get itched in your head that one of them is 10 to -3 and the other one is 10 to -3. And if you manage to remember this, then you would remember that new air is 10 to -5, because if water has already got 10 to -6, then it must be that the air will take the other one, 10 to -5. Okay. So kinematic viscosity of the air is 10 to -5. So whether it's water or air, the kinematic viscosity is really small. And so they are not really that viscous, like water and air is not really that viscous. And that's why we have this concept of boundary layers. Only a very small place near the wall have the viscosity effect. It's called boundary layer, but outside it's almost invisible. So water flow and air flow outside the wall is almost invisible. Okay, so and then I'll put this note 354 October. Good. So he gave us the viscosity, and by the way, that viscosity, which is a dynamic viscosity, which is the mu, can also, you will find it commercially measured in, rather than Pascal second, measured in, yes, centipause. And the kinematic viscosity, which is meter square per second, usually commercially is available in centistokes, which is like millimeter square per second. All right. So we have the viscosity and the density, and he had the flow rate, and he's basically telling us, and the cross-section area, and he said determine the pressure drop. So that is the first time. That's basically, let's use the formula. Delta B is FL over D half rho V squared. Except the only problem is, what's the problem now? It's not circular. I have to use this rectangular thing, and I have to use the hydraulic diameter. And F is not 64 over the Reynolds. I have to go to that table and figure out, you know, because it's probably going to be laminar, it's not going to be turbulent at that small diameter. I better figure out What is it? Where is it? Yeah. I need to figure out which one of those I should use. Is it 60, 96, or 62, or 57, depending on A and B? What is the ratio between A and B? Right? Huh? I can't hear. So 1/3, right? So it's going to be 0.33. So we are like almost here. So maybe it's going to be 64 after all. Maybe that problem is cooked so that we can get exactly 64 over the Reynolds, huh? For 0.33. For big duct, but I mean, look at this problem. This is like leakage. I mean, it's 1 millimeter by 3 millimeter. Who designed a duct that's 1 millimeter by 3 millimeter? So that problem is probably some kind of like leakage in a bearing or something, very, very small film. But most problems real problem are turbulent flow. Yes, I stand with my earlier remark. Most problems are turbulent flow, except for like leakage flow and cleaving. They call them cleaving flow. So the flow is so small, because it's just like oil going from a tiny space. But the other complication here too, although it's a simple formula, is that this is parallel flow or series flow. They are in parallel. All of them come from one place, leave to the other place. So then what will happen? The Q, the 30 millimeter, will get divided over all of them, but they all have the same pressure drop, right? So I mean, I can solve only one of them and get that pressure. One of them with only 5 millimeter cube per second. That works. So you solve one of them, and that will be exactly this pressure, right? And so you can see here, you're saying, well, I need to use, let's use a stable, Let's use a stable and figure out what's our hydraulic diameter, right? So you're gonna do this, I guess, and find out what is the equation that you would use, and you would say that delta P is half rho V squared multiplied by FL over D. And you got your length, you got the hydraulic diameter for this one, you'll be able to calculate the pressure here compared to this. Note that he's saying the same elevation. So the Z1 will cancel with the Z2. And so the pressure here, if you say this is pressure 0, because you're using gauge pressure, then you're going to calculate B1 gauge. Question about this? Good. Now this one, this is where you have now not just parallel or series, but now it starts to become kind of a network of pipes, and it can get even more complicated, like this, when you have multiple, exit and multiple pipes. So the way to solve those things is to nail them down to the elements. The elements here is the junction and the pipe. And so each one of those is a pipe. And what's the pipe equation? Delta P across that pipe is half rho V squared times FL over D. So there is a relation between the delta B across the pipe and the velocity inside, or basically the flow rate inside, because the velocity and the flow rate are the same, meaning Q is AV. So I mean, I can remove the delta. When I'm saying the delta P, when I say the delta P is half rho V squared times FL over D, I can easily remove that V squared and write instead half rho and then Q squared, right? Q squared over area squared. because again, the V is simply, the Q is AV. Right? And then just multiply by FL over V. So then there is an equation between delta P and the Q square. There's an equation between the delta P and the Q square for every one of those branches. Of course, you know, this guy is a big deal, but for now, let's just assume constant F or something. Let's make our life easier a little bit, and then we can make it more complicated later on. So for every one of those equations, there is a relation between its Q and its delta P. Here, the delta P and the Q. So then at each one of those junctions, you can say here's P1, here's, or like P1, P2, P3, P4, P5, P6. Every one of those junctions, there is a pressure, and every one of those branches or pipes, there is a Q. Okay? And across every channel, this P minus this P equal to that Q. And in every one of those junctions, this Q equal this Q and this Q. So before you know it, you will have a system of equations that relate all the pressure and all the Q together, right? You get something like this. Q, 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 right? All the Qs and all the pressure, right? And you will write this big matrix, matrix between all this equation together, and you solve them together. What is annoying, and there are programs that actually just solve those network of pipes. What is annoying mathematically is that Q square. Has this been delta B and the Q, it would have been piece of cake. It would be a linear system of equation, and MATLAB can fly like this through them. There is, like, if you remember 13, remember all the matrix inversion technique? I mean, we can just invert it one time, and you get A minus 1, and then you have a relation between delta B and the Q. Like, you change the Q, you get the delta B, like they're just by multiplying A minus 1. But what's annoying is that Q square. So a lot of software do what? Linearize this equation. They would say, you know, this Q can be like 2 Qs. Q multiplied by another Q. And the first Q, let's use it from our initial guess or previous iteration, or so they assume a Q. Now there's only one Q in every equation, or Q1 and Q1, and multiply plus Q2 plus Q time Q2. All those Qs in the big matrix, it divide in two parts: Q known, kind of, or assume, and the Q that you're solving for. And so now once you realize, you can fly through them, get the solution, and go one more time, and one more time. And every time you go, you update the Q that you are assuming, and you solve for the other one, until what you assume is what you get. Okay? Make sense? So let's solve this, but with our pencil and paper, we can only solve like an easy one, like maybe you know, 1 junction, 3 pipes, that we can do with our pencil. But any more than this, you really need to like a computer to set for and iterate for you. All right. So in a system like this, the Q1 here is basically a node. What happened at that node? Q get divided into Q2 and Q3, right? And that the pressure from here to here is the same as the pressure from here to here. And I know that you are probably worried about the hydrostatic pressure, but you shouldn't. Let's start. I mean, let's think of it as a horizontal problem. Think of it as basically just we are going into you know, the first floor, or like a ceiling network of sprinkler. So you are delivering at the same location. So that pressure will be that pressure. That's why he said HL2 is the same as HL3. Why HL2 and HL3 is the same? Because they start from this node and they finish at the same location. Again, think of it as horizontally for now. Like we are looking from the floor, from the ceiling to the floor plan. Okay. So it opened the same tank, therefore it has the same pressure. Okay. So and he is telling you will calculate the, say, the flow rate for me, and the pressure in the middle, for example. Because say this pressure is, this head here is like 10 meter and this pressure is 4 meter. So how it will go. Right? So you can see how he's writing the Bernoulli equation along this branch and then along this branch. Right? So when you go from here to here, you got the pressure over here, the velocity over here, which is 0 plus that elevation, equal to the pressure here, PP, plus the velocity, plus the elevation, plus that H loss, plus this H loss. That is the losses, and that's why you are putting it in the outlet, right? In the outside. And going along this branch, the energy here is lost over what? The energy at 1 plus the energy at 3. So I see two equation, and I already see 3 unknown now. I see Q1 and Q2 and Q3. Where is Q1 and Q2 and Q3? It's inside HL1 and HL2 and HL3. That HL is FL over D half rho, their V squared over 2G, and their V squared is their Q divided by their area, right? So you can see over here. So here is V2, V3, V1, V3. And you can see how he canceling the pressure. He say this is the ambient and this is the ambient. Well, it's different problem for the pressure, but it's the same equation. When you look at the equation, it's exactly the same, right? This is also difficult problem because then he's not really sure whether that flow rate will go this way or that way. So the point is there is 3 velocity that we need to solve for between this and this. Yes. And so 3 unknown cannot be addressed with 2 equations. That's why you need a third equation. So the third equation comes from the node. That node say that this Q equal to this Q plus this Q. Right? And so now you finish basically the 3 system. So 3 equation and 3 unknown. So what we did here, knowing the pressure here or the static pressure here, static pressure here, static pressure here, and having the node equation, and this, when you think about it, this is similar to the pipe and the pipe and the pipe equation. Each one of those pipe equations is basically saying my flow rate or my H loss is due to the pressure difference from this place to that place. Except that he did this and he did this. So what we did here on a small pipe, they can easily do it on, in a big network. It's the same concept, same set of equations. Right? So this part, whether the flow rate is going to go this way or that way, you don't really know at the beginning. Same thing over here. I mean, you should ask yourself, well, does the flow really go this way or will the flow go that way? I mean, depending on those values at the boundary. So what should we do? We should assume the flow and let the equation get the velocity for us. And if we are right, it will work. And if it's not right, we know that it was wrong and let's go the other way. So in this example, over here, those three reservoir, and we are not really sure about that direction. I mean, we are sure about this for sure, and we are sure about this. There is no way that this guy will go up, right? There is no way that Q1 will be going up, and there's no way that this guy will pump the water up. But it's this guy. Is he going to go this way or going to go that way? So it really depends on the pressure here compared to the pressure here, right? So what is required? Determine the flow rate into or out of each reservoir. The unknown is Q1, Q2, and Q3. Okay. So same node equation as before. This Q plus this Q. Why plus this Q? This is just the assumption. I mean, right now we are saying Q1 plus Q2, but in case this didn't work, we will flip it. And we'll make Q2 going the other way, and we'll solve for it in this other configuration. Right? So you make the best guess that it's probably coming in. And so then the equation become like this. So this plus this equal this, okay? And so if this is now the new direction, you can see that the equation from B to C has pressure drop on 2 plus pressure drop at 3. And the other equation is from A to C has pressure drop here plus pressure drop here. Has this been done this way, we would have written the equation like this and an equation like this. Yes. If the Q2 was going into the reservoir, the pressure drop from A to B would be lost over this pressure drop plus this pressure drop. And what's the pressure drop? FL over dV square over 2G. FL over dV square over 2G. Note that he's writing it in the form of this Bernoulli equation is written in terms of head. So when you're writing it, then this is P over rho G and V square over 2G and Z. So we can write Bernoulli equation in terms of pressure. Bernoulli equation can be written like this: P plus half rho V square plus rho GH equal constant, or equal the energy at the other kind. The unit for this is Pascal. Or you can divide everything over rho G, and it will be P over rho G plus 0.5 V square over rho G, not rho G because the rho cancel with the rho over G, plus H equal constant. And what's the unit now? Well, units is meter, right? Or feet, depending on whether you want to use this. And the one that we don't really use it that often, but it's nice to remember, P over rho plus 0.5 V square plus what? Plus help plus GH. And the unit for this one would be free quiz if you tell me the unit. The right unit in my head, not the unit that you see for me, because you could easily say meter square per second square. I don't want that. I want you to say what's the unit? Free quiz, guys. What's the unit? Come on. Anyone? Gallon per second, no? Joule per kilogram. Why joule per kilogram? Power was m dot gh, joule per kilogram. Joule per kilogram. GH is joule per kilogram. GH is joule per kilogram. The head multiplied by G is the energy per unit mass. Why is that also like? Because 0.5 V square, what does it remind you of? What does 0.5 rho square remind you of? Huh?
Kinetic energy.
Per unit mass. Kinetic energy per unit mass. Kinetic energy is half mv square. So half v square is not joule, joule per kilogram. So yes, v square is meter per second, meter square per second square, but it's also joule per kilogram, right? So everything here is joule per kilogram, right? This is all energy per unit mass. So Bernoulli equation can be written in terms of pressure, in terms of head. That's really nice for like when we do pump and stuff, but it also can be written in terms of joule per kilogram. And so when I look at this, I see potential energy per unit mass. What's potential energy? mgh. So m is missing, that's joule per kilogram, potential energy per unit mass. I see half v square, that's kinetic energy per unit mass, and I see p over rho, which is the flow work, the one that we add to the u to have the enthalpy. H was u plus p over rho. So that tell you p over rho has to have the units of enthalpy, and it have to have the units of internal energy, right? Because what I'm saying is that H was U plus U now is the internal energy plus P over rho, right? And the unit was joule per kilogram. Wouldn't it be nice if we study everything in Latin? That would be awesome. Joule per kilogram. So H is U plus P over rho, joule per kilogram. Okay, good. So they are writing it here in terms of meter, right? And that's why it's meter, 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 meter. Everything is a meter, including the. So don't write the pressure loss here as FL over D half rho V square. No, you have to write FL over D V square over 2G, right? So basically between those three guys, it's three equations in three unknown, V1, V2, and V3. And so he can, that the rest is like mass, you know, like he's just pulling them together so that he can get the V. And notice that all those F are assumed. I mean, you cannot really get the F without knowing the V. So you have to assume an F, get the V, go again, check, iterate and iterate and iterate until the F that you are using match the velocity that you are calculating, right? So he's solving this. He basically, three equations, three unknown, he turned them into only one equation and one unknown, which is V2. And he solved it, right? And he figured what is, this is how he turned that. I'm showing you the steps. And he basically have a first order, which is second order in V2 squared. He solved it and he basically figured out the solution. So that's V2, and then he got himself Q1 and Q2 and Q3. If he didn't get a real solution, then he would say, oh, Q2 must have been wrong, and then he would go back. All right? Make sense? Okay, so before you do your quiz, I just have one comments. Let's go solve quiz, the previous quiz. I posted the solution for it here. So let's just visit it before we do the today quiz. Quiz 7 solution. What was quiz 7? He said plot a Rankine cycle with reheat and open feed water heater. The problem I saw in this, like there was only two people that I liked their solution actually. So Bibin graded all of it, but I had a chance to look at all of them. And I mean, say quiz 6, but it was really quiz 7. And what I saw was wrong was, by the way, this is not the only solution. See how he's doing what? He's doing the reheat as the same as, the pressure of the reheat is the same as the feed water heater pressure. That's okay, but not necessarily. I mean, we can do the reheat like this. By the way, we know what's the optimum reheat pressure, right? The reheat pressure to be optimum, it should be like 0.75 of this. And what's the optimum feed water heater pressure? If you are the one selecting that feed water heater pressure, where do you put it? You put it up here or down there, or where do you put it? Huh? No, that is the reheat pressure. But the feed water heater should be the feed water heater, the steam that we are pulling to heat our water from 2 to 3. Where should we put this ideally?
0.5,
Yeah, in the middle. In the middle of what? In the middle of this
top and bottom pressure.
and this. Right? Like you come to the TS diagram and you basically set them in the middle and you put the, is it really the ideal? No, but it's really a very good start. Then you iterate on the cycle. So what do people do wrong? The pressure line, I still saw people, when you come to the pressure, look at me, they come here and they do what? They keep going. The pressure line, once you leave the dome, what happened? You go up. All those are constant pressure, right? I want you to make sure that in today's quiz, you go up with the pressure. Don't keep straight. This part, if you are plotting a sketch, you should make the pressure or the pressure rise in the pump showing up. Of course, in real life, we know that this line, the pressure here and the pressure, they are all very close to the curve, right? But for a cartoon that's trying to explain where are the pumps and where are the states, you need to show it up to us, right? Make sense? So 2 mistakes. Pressure line, when you leave the dome, go up with it, don't stay flat. And also, when I say ideal Rankine cycle, what does ideal mean?
No losses.
Isentropic expansion. So when I say ideal cycle, you don't plot it to me like this. You need to go down straight. Isentropic. Yes? Okay. So just because I think this is really important, and maybe it will show up in the final, let's have one more quiz on this. So if you go to assignment, let's see if I like them this time. So in assignment, if you go to quiz 8, which is today, right? And you download this, it will tell you, sketch the power plant corresponding to the attached TS diagram. So here is your TS diagram, and I want you to plot the sketch, you know, the boiler, the turbine. How many turbine? 2 turbine, right? And how many feed water heater?
2.
2 feed water heater. And I'm not going to say whether they're open or closed. You have to look at this figure and see which one is open and which one is closed, right? And put the numbers. Right? And I think you have until 8:30. Is that correct? Yeah, so we have a lot of time. And actually, this is only 20%. You get 80% just saying whether you are in class or you're online. If you don't say this, you lose 80%. So please write this. 80% for being here or online, and 20% for making the cycle with all the elements that correspond to this figure. when you plot the closed feed water heater, you need to make sure that show that the pipe inside is like constant, like going by itself, and the steam coming from like the rectangle, huh? But the open feed water heater is like a box where everything come and one guy leave, right? So make it show up. Question from online, will it matter how the queues are labeled, or should we only be concerned with making sure that all the queues are considered? I think that is not the quiz. I think Nick was asking about the example we are solving. Right? Yeah, so it was the example we are solving. Yes. Yes, so to answer that, we need to make sure that all the queues are labeled, of course. But whether they are going right or left, it doesn't matter. As long as you write the equation of the nodes according to those directions. And you let the equation tell you which one is plus and which one is negative. All right. And I'll see you next week. Remember, you have until 8:30. Don't stay beyond 8:30.